Alright, today we're going to be going over this A1990 that randomly stopped turning on, and the purpose of this repair is for data recovery. So this machine has some very critical data on it, and the only way to get data on this machine is to get it to boot. So without getting this board to work, there is no data. So if you go to a traditional repair shop, they'll offer to replace your board, or if you go to Apple, they'll replace your board, and that leaves your data behind. So we're going to try and figure out what's wrong with this board on component level and see if we can fix it. So the first step to diagnostics is always seeing what the board takes on our USB-C amp meter, because that'll give us a rough idea of where the board is getting in its power up sequence. So it looks like about 5 volts. Let's give it a second, because sometimes it will jump to 20 volts. It's at 20 volts, 0.02, 0.14, 0.11. It looks like now it's at 0.116. So already this is telling me that the board is getting somewhat into its power up sequence, but it's encountering a problem. And one key characteristic of letting us know if the board is running into a problem is when the amperage goes up, and then it drops, and then it goes up. So it just went back up to 0.10, 0.12, 0.18, whatever. Then it drops down to 0.01, 0.02, because there's an issue somewhere in that power up sequence. It encounters an issue, it shuts off, it retries to see if that issue has resolved itself. It hasn't, so it just is in an endless loop. So this can be caused by a multitude of factors. The first thing I'm going to want to check on this board, because this is very, very common, is the SSD 2v5 NAND regulator. So I want to go ahead and check voltage on that. I want to see if it's outputting 2.5 volts to our NAND, because in order for this board to boot, it needs to load something called BridgeOS, which is basically the operating system for the T2 machine that's on our stored on our NANDs. So I want to check voltage and see if our NANDs are getting power here. I do suspect they will be, but I want to double check here. So looks like I have 2.5 volts. Good. 2.5 volts. Alright, so this chip is not dead. This chip that I'm measuring right here, which I'm going to show you guys under the scope, is very, very, very common to fail. So it's very, very common to fail, and it usually fails in a way that ends up sending its source 12 volts into the NANDs, which will kill them and result in complete data loss. So this is the chip in question right here. Alright, these really commonly get corroded just from dust in the air, and those usually lead to this chip shorting its input voltage to its output, which is very, very bad, and that kills our NANDs. This area is unremarkable, but it is a good sign that I have 2.5 volts here. So carrying on, I want to check what PP-bus G3 hot voltage is. And there's a few things that PP-bus G3 hot will tell us on a T2 machine. So if I have 12.6 volts, BridgeOS is pretty much loaded, and that means our T2 chip is mostly working. Now there's some very remote scenarios where you can be at 12.6 and have an issue there still there, but 12.6 gives us a good idea that our T2 is working at least in some fashion, and it is at 12.285. Interesting. Okay, so that right now it's at really low amperage. It's at 0.3. It just spiked back up, and now I'm going to check it again, and now it's at 2.5. Very interesting. So let's go ahead and take a look at something. I'm going to use the trend feature of my multimeter here to kind of show you guys what's going on here. So we're going to go record. Now this is the Fluke 287 multimeter. It's a little bit expensive, but so far I'm absolutely loving it. I'm going to go ahead and just log voltage on PP-bus G3 hot for 1 minute. So I'm just going to hold my leads here, and we're just going to watch this. So it's going to go for about a minute. And I just want a graph to visualize so I can show you guys what's happening with this voltage. And the whole thing to take away from this is this drop in voltage is correlating with our amperage drop. So when our amperage drops down to 0.0 whatever, that voltage also drops, which tells us our T2 is kind of, it's either it's rebooting or something funny is going on there. So okay, now it just dropped to 5 volts. I think it's because I just bumped my USB meter, but okay. So we're going to stop this, and I want to show you guys the trend. And what you can see here is, so this is kind of going to be hard to visualize here. So I'm going to try my best here to show you guys, but there was a drop right about right there. It just drops down to 12.2 for a brief second, comes back up. So that's interesting. Something's going on in our T2 circuit. So something is definitely amiss there. So let's check. I'm just going to start checking common things that I kind of have seen before. And one of those is going to be PP5V S5 LDO, which comes from this chip right here. On this cap, I've seen this cap short right here. And it looks like we are plug in my USB amp meter properly. So this is missing for the time being. So, alright, now it's present. So we don't have a short there, but something is definitely amiss in the power-up sequence. PP5VS5 is another one we could check, or PP3V3S5, and that's going to tell us somewhat if our board is attempting to power our PCH. So we're going to check that next. Basically, I'm just feeling around to see where we're at in the power sequence. And that is missing. Okay. So let's talk about something for a minute. We have 12.6 volts. At least we have 12.5 volts. That means our T2 is somewhat working. It's communicating to our ISL 9250 or 9240. It's somewhat trying to boot. We have power to our NAND, so short of our, or at least to our right side NAND. So a short of a NAND is pretty unlikely at this point. It's still possible, but it's kind of unlikely. A short on PP bus is ruled out, obviously. A short on PP3V3S5 is rare. A short on PP5VSO is also rare. So one thing that we see with these boards, specifically the A1990 and A2141s, is thermal imaging is highly specific for issues. Meaning specific means it finds a lot of issues that you wouldn't find easily unless you spend hours measuring stuff. So I think at this point, given its weird cycling-like phase, I'm going to go ahead and thermal image the board and see what we find on it and see if there's anything just to rule it out. Because thermal imaging has a potential to save us a lot of time. It's easy to do, and it takes very little time to do it. So we're going to go ahead and give that a shot right now and see if we find anything that is of interest. Okay, we're going to go ahead and take a look at this board under the thermal imager. So this area of heat right here is from the T2. This is normal. Don't think you have a short on your T2 because you see this. This is totally normal. It is a CPU, so it will get hot. Our PMIC looks good. There's no sign. One really characteristic fault of a T2 issue is you'll see not only heat on the T2, but you will see one of the inductors on your PMIC getting hot as well because of the current it's pulling. So we're just going to carry on and continue scanning this way. Normal heat from our PP Bus G3 hot coil. Those will get hot. That's why they have a thermal sticker on them. Oh, that doesn't look right. So that stands out. Okay, but if we look at this, it doesn't really look like it's coming from this side of the board. So we could zoom in here. We're just going to zoom in really close. Let's position this. And we could, with a high resolution camera like this, we can often tell where our short is coming from on the side, which side of the board it's on by just looking at this. So I'm going to go ahead and adjust my focus here to get the perfect image. Alright, so there's heat coming on from the other side of the board. It's none of these caps there because you can see those guys pretty well. So what I'm going to go ahead and do is flip the board over and see if we can see anything in that area on the other side of the board. So I'm going to flip our board over. We're going to plug it in, and it came from right around this area right here. Okay. Right around here. So there's capacitors there. There is a chip right around here and a coil. So we are going to go ahead and look. So this is our left side SSD 2v5 NAND because there's NANDs on both sides. So let's go ahead, plug this in, see if anything gets hot here. There we go. Look at that. So look how that stood out. That capacitor is getting very, very, very hot, already at 130 Celsius in a split second. So that looks like it's going to be our issue. Again, thermal imaging for issues like this where there's low amp draw, it is absolutely imperative. It's very, very highly specific. It finds a good amount of faults. And here's another example of that right here. So now we actually have to fix what's wrong. So let's go ahead and look at this area here. So we see we have a capacitor right about here. And if we look at it, we could actually see it's in pretty bad shape. It has a crack in it and there's discoloration on it. So notice we have three guys right here. We have these all look normal, and then there's this one that looks really, really ugly. So let's take a look at our board view and see what this looks like. So on our board view, we're going to pull this up and look here. It looks like it is on PP2V5 NAND SSD 1. So we're going to talk about replacing this caps because I have had stuff destroyed this way as well. So here is our capacitor right here, okay, that's shorted. This is on our NAND power line. We have our NAND right next to this capacitor that is underfilled. So let's look at how this capacitor is used in the circuit, and let's determine if we should put it back. So this is a decoupling capacitor on the output of the capacitor. It's a 20 microfarad, and it is marked critical on this. So critical, so here's my rule. Capacitors like this, decoupling capacitors, do not have to be replaced every single time you remove them. They're not required. They're just there for smoothing, and devices get along just fine if you remove half of them, honestly. So if we just take off one, chances are everything's going to be totally fine. If there is a capacitor marked critical and it's a decoupling capacitor, it's technically not critical in an electronics engineering aspect of things. However, if something says critical, I try to replace it. If something does not say critical and it's just like a 0.1 microfarad capacitor, take it off, don't worry about it, you're good to go. However, this is critical, and this is to smooth the power for the NAND chip. So I do want to try and replace this. If I left this off, it would be totally fine. It'll get along just fine. Nothing is going to happen. But given the fact it is marked critical in the schematic, I'm going to try and replace it. Now, we do have to take consideration and caution when doing this because we are so close to our underfilled NAND. So first off, removal. We're not going to use hot air to remove this guy. I'm going to get my tweezers, and I'm going to work it back and forth, just like that, just like pulling a tooth. Comes right off. All right, just like that. So I'm going to get my iron now. We're going to clean this up. A little bit of flux and solder. My iron is heating up. I'm going to get a little bit of flux here. Definitely in a tight area. Main thing is I want to get this, gotta increase our temperature up here. I'm gonna go full on 840 for this. I gotta get those pieces of the capacitor out of here. So there's pieces of that capacitor that really need to go. And let's see. It would actually help if I actually set my iron to 840 instead of just leaving it there on the prompt. There we go. Look at that. Beautiful. So there's still some pieces there, so I'm just going to work these guys out with my iron. Just like that. And there shouldn't be anything left there, but we're going to wick the pads. Beautiful. So those pads are wicked. Let's clean this up. A little alcohol. Okay. Gonna put a little solder. on these pads, a little bit of flux. It's not necessary to ultrasonically clean this board because it is fairly clean, just dusty, so it'll just get dusted and a little bit of new thermal compound as usual. Okay, there's that. Don't worry about making your joints too clean in this phase because we're going to use hot air to put this capacitor on, and it's going to flow really nicely. So I'm going to grab a donor board here. Got to find a donor board with these capacitors on it, so time to dig in your pile for an A1990 board. We have so many A2141 donors, and the A1990s looks very, very similar, so sometimes you might have to dig a little bit. And that's okay. Alright, we have our capacitor localized on a donor board. I'm going to go ahead and use my 6mm bent tip nozzle for this. So that'll allow me to direct the air a little bit better to blow it away from the NAND. Go ahead and pull this off. So you do notice with the bent tip nozzles, it does cut down on that energy pretty significantly, and it does take a little bit longer to heat soak it, to remove it from the donor board. And I'm blowing my air away from my NAND, just like that. And this is now in place. So what I'm going to go ahead and do is just clean this area with alcohol. We're going to get this board dusted and then apply some fresh thermal compound, and then this should be fixed. I guess we should probably make sure this works first before doing any of that, but I'm pretty confident this will be fine. So we're just going to clean up the critical areas. I just want to clean mainly the 2V5 regulators because those are the most common areas to get hit by dust and liquid. Yeah, these are really, really common, and as far as these go, I think what we're actually going to start doing is conformal coating these areas on devices that come in, because this is risky just leaving it. It is very concerning that Apple came up with this design. I have a dedicated video I need to edit on this, but yeah, this area can be really, really commonly hit with liquid, and not just liquid, just dust, and cause issues like that. So I think what we're going to do on all these A1990s is start conformal coating these areas to prevent this whole thing, the future failure of this one chip if it gets dusty. So just want to make sure it's really clean right here, and I'm just going to go ahead and put a little dab of conformal coat on it just to prevent that possible future failure happening. We're actually going to do that after we dust it there, so we'll be right back to put that on. Okay, I just set our board back in the enclosure briefly before we do any conformal coating or anything else. I'm just going to plug this in real quick, and we're going to see if this turns on. So 5 volts, 0.23, 0.20. Alright, I do have trackpad click. That is a very good sign here. And it looks like here, let's see. Some A1990s are really, really picky about their battery being plugged in. This is a 96 watt, so we're going to go ahead and plug in our battery and see what happens. Because it still has low amp draw, but it's a little bit different, which makes me kind of think it wants our battery. They introduced a firmware update, either with Big Sur or Monterey, that stopped that from happening. But it still might want our battery. So we're going to plug our battery in. There we go. And we're going to attempt to turn this on one more time. 5 volts, 0.24. 20 volts, 0.38. 43. 0.50. Definitely different than before. 0.71. Okay. So it still looks like it's not turning on. Interesting. So we're just going to watch that. That makes me think, so I'm thinking, this got shorted to ground. So we have had a short to ground. If voltage to the NANDs was lower for a second, that could have possibly forced it into DFU or caused firmware corruption. Or it could have damaged a regulator. So it's very rare, but sometimes you can have damaged regulators and damaged resistors from shorts to ground like that. So we're going to go ahead and open back up our board view and try and figure out what might have happened here. So first off, I want to see if we're getting any voltage on 2V5 NAND now on this side. So we could easily measure that. We are charging the battery. That is different than before. Was not doing that in the past. So let me get this on. All right, and 2V5 NAND voltage is can't see it there. Got to turn it towards me. .5 volts. Okay, so we do have NAND voltage now. So that's a change. What about from our PMIC? 1.8, 0.9, 0.9. Okay, so everything seems to be working just fine here. I don't see anything at this point electrically wrong, other than the fact it's not booting. So this makes me think something happened when that capacitor shorted. What caused it? What did that capacitor cause? So this makes me think it's in recovery or DFU or something like that. So we do have battery voltage. I'm going to go ahead and plug it into my machine right here and see if this is possibly in recovery or DFU mode, which can happen quite frequently when you have issues like this sometimes. And it is in recovery mode. Imagine that. And the reason why it is most likely in recovery mode is this was brought to the Apple Store first. The Apple Store most likely attempted a DFU revive, which failed because our NAND had an issue, which resulted in this happening. So hopefully our data is still there and the Apple Store did not ruin our data. So we're going to hope for that. So I have my recovery console right over here. You guys probably can't see this monitor. Yeah, you guys aren't going to be able to see it. But I'm going to go ahead and open Apple Configurator 2, and we are going to see what we can do here. So revive device, not restore. And we're going to see if this works. So it says installing system. And we should get some signs of life from the device relatively quickly. Just switched over, so that is a vital part. It goes from DFU to recovery, recovery to DFU. So that is a very vital part of our process here. And I should get fan spin very shortly here if everything moves along. We don't want to touch it. We don't want to touch our trackpad, anything like that. And we'll be right back after this is done with its restore process. This process can take anywhere from 2 minutes to 30 minutes, so it's no sense having that all on camera. So this is installing, and hopefully, actually, we just got a spinning fan. So as we're waiting, we just got a spinning fan. And with any luck, an Apple logo is going to pop up on the screen. So that is very good. So yeah, diagnostics and figuring out how stuff happens is a very fun part of this job, because the user did go to the Apple Store first. They replaced the top case and the battery, and then they said it had a logic board issue. My guess is they did try a DFU restore. It did not work because half of our NANDs weren't working, and it failed, which forced it into recovery mode. Anytime you see a device in recovery mode, it typically means a DFU restore was interrupted or failed in some way. And in this case, it does have an Apple logo, but we're going to wait until this is fully booted and then go from there. All right, so we're done with the DFU revive. Luckily, the data is still retained, the device boots, and we can give some happy news to this customer. But all looks good here. Now we're just going to go ahead and put a little conformal coat on our 2V5 NAND regulator and reapply our thermal compound, and that's pretty much it. This is good to go for the next foreseeable future, really.